about that for a second, okay? Ionization energy, and it was on that, like it does relate to those photoelectron spectroscopy graphs that you looked at, okay? Remember on those graphs, you could tell like what the peaks were, right? And if this said 7 and this said 3 and this said 1, what does that tell you about the location of this peak? Like, which electrons are those? Which sublevel? Probably. S. Which S? 1S. How do you know this is 1S compared to this one?
It's the first one.
Well, not only is it the first one, but highest number, which correlates to energy, right? Which probably means that these are closer to the nucleus and harder to remove, right? Okay. That really gets to the concept of ionization energy. Ionization energy is how much energy do you need to supply the atom to get it to give up an electron, okay? Now, for all of the atoms, which electrons are going to be the easiest for them to give up? Valence electrons, okay? Now, let's look at lithium for a second. So lithium is, we already discussed, 1s2, 2s1. 1. Okay. What does lithium want to do? It wants to give up an electron. Are you going to need to supply it with a ton of energy to make it give up an electron? No. It wants to give one up anyway. Is it going to give it up for free? No. But it's not going to make it that hard for you to get the electron. Give it a little energy, it'll give you the electron. Getting rid of this electron is called its first ionization energy. Okay? Because what if I want a second electron from lithium? Is it going to give it up as easily?
No.
Does it want to give up one of these? No. It finally got what it wanted, right? It's not going to want to give up one of these. To get it to give up one of those is called a second ionization energy. And it's a whole different amount of energy that we're talking about. To get it to give up its third would be its third ionization energy. So every single electron in the atom has a certain amount of ionization energy associated with it. When you learned ionization energy last year, you probably only learned it as like a flat concept and not like each atom has multiple ionization energies, okay? So let's talk about fluorine for a second. We're going to go all the way across. So here we are at lithium. Let's go all the way across the row to fluorine. Fluorine is 1s2, 2s2, 2p5. What does fluorine want? To gain an electron. So how do you think fluorine is going to feel about losing one? Does it want to lose one? No. So compared to lithium, what's its first ionization energy going to be like compared to lithium's? Higher. Because nonmetals are looking to gain. They're not looking to lose. So you're going to have to supply this with more energy to get it to give up an electron. Does that make sense? Okay. So that's what they're talking about on this slide about like first ionization, second ionization. Okay. And if you look at this chart, which I just want to point out to you for a second, because honestly, right here, remember where I said like there's a bunch of questions that pop up on the AP test about trends? I've seen charts like this pop up on the AP test, okay? It's a good chart because this, you guys, is officially data, right? This is data right here on that slide showing you ionization energy values. This is putting this concept into context, okay? Sodium wants to do what, electron-wise? Lose one. So it'll give up one. What happens if you try to take a second one? It wants like 10 times more energy. So what does that tell you about what charge the sodium ion probably has? Yeah, a plus. This is likely to be Na plus, but not Na2 plus, right? It doesn't want to give up a second one. That's why sodium has a 1 plus charge, okay? They will ask you, just so you know, they will ask you about an atom you're not super familiar with, or they'll like call it element X so that you don't know who it is. And they will give you data like this, and they will say, like, what charge do you think this ion has based on this data, okay? Look at magnesium. Can you justify why magnesium's a 2 plus but not a 3 plus? Yes, you can. Now, this is all in the third period. In general, what happens in general as you go down, or as you go left to right on the periodic table? What do? They increase, okay? There's a couple of blips on here, though. What are the blips?
Between phosphorus and sulfur.
Phosphorus and sulfur is a little blip, and Mg and Al is a little blip. Do you see that? Okay. Do you remember when we talked about the orbital diagrams, and we were talking about how, like, especially with the d electron, or with the d atoms, that they really just want to like make the most stable arrangement they can given their situation? Well, keep in mind, Mg looks like this, right? This is where Mg ends, correct? Aluminum, on the other hand, has this plus net. Okay? Why would Mg put up more of a fight over losing one of these than aluminum does over losing this one?
Because that box isn't full.
Right, like, this is a disaster, right? I mean, aluminum really doesn't care about this at all. But what does magnesium have going for it? A full sub-level, not even just a box. Like, that's the S sub-level, isn't it? And magnesium has a full S sub-level, naturally, which is a somewhat stable arrangement, okay? So that's why it puts up a little bit more of a fuss than aluminum does, because it's like, well, I don't know. I mean, I want to get rid of these two, but it's really not that bad. You know, like, I at least have the full S. Now, I'm going to change this from aluminum to phosphorus, okay? Here's phosphorus, right? And then compared to phosphorus, we have sulfur, which has one down. On the graph, it says that there's a little blip there, that it's actually easier to get that electron from sulfur than it is to get this one from phosphorus. Why?
It's happier with the half full.
It's half full, and we're maximizing spin. Remember Hund's rule? Maximize spin. They're all spinning up, right? So phosphorus actually has a somewhat stable arrangement going on its own, where it's like, I don't know, this is pretty good. I'm not really that excited to give one up, okay? Whereas sulfur is like, yeah, take the down one. Like, let's just get rid of that, okay? I mean, really, I want to gain, but take the down one. It's not the end of the world, okay? All right. Are we going somewhere?
No.
Okay. So, that's that. Why does ionization energy decrease going down a group? We talked about across a period. Why does it get easier to take an electron away when you go down a column?
The distance from the protons increases.
Yeah, they're farther away from the nucleus, right? Like whether we're talking lithium, like if we're talking lithium who has one in 2s compared to sodium who has one in 3s, which one's further from the nucleus? 3s. So this is going to be a little easier to pick off than that one, isn't it? Okay, so that's why. All right, go to 269. Okay. And look at this sample exercise on 269. Okay. It says 3 elements are indicated in the periodic table in the margin. Which one has the largest second ionization energy? So you're looking at those colored blocks. There's the red one, the blue one, and the green one. Okay? They're asking which one's going to have the largest second ionization energy. Which means what? Does it want to give up a second electron or no? No. So which one of those would have the largest second ionization energy? Not green.
Red.
Let's look. All of them. Let's look at who they are for a sec. Who is red? No. Sodium. Who is blue? Calcium. And who is green? Sulfur. Okay. So, first of all, let's look sodium and calcium for a second. Okay. Now they're not exactly in the same row or column, but close enough. Okay. Who's going to be easier to get away from in general? Calcium, because it's farther from the nucleus, right? Okay. Now, look at sulfur. Okay. It's in the same row, right? It's in the same row. Now we're talking giving up 2. What does sulfur want to do in general? Gain. Gain how many? 2. So let's say we get sulfur to give up 1. Okay? If it gives up 1, how do you think it's going to feel about giving up a second one? Not good, but it's already moving in the opposite direction of its goal, correct? Okay, look at sodium. What does sodium want to do? Lose 1. If it loses 1, it has everything it ever wanted in life. Okay? What if it gives up a second one? It lost what it had and always wanted. Right? Because now it's like fluorine. It's not like neon. Right? And those electrons are closest to the nucleus, correct? Like sodium's the smallest one no matter what. It has the largest second ionization energy for sure. Okay, do practice exercise 2. Same logic. It says which has the greater third ionization energy? Which has the greater third ionization energy? What's the answer going to be? Where's calcium? What does calcium want to do? Lose 2. Is it going to want to give up a third? No. Okay. Not only that, but if we look at the calcium, let's talk about that for a minute, okay? Let's talk about Ca2+. Okay, let's talk about Ca2+ for a second. Ca2+ has 20 protons, correct? And 18 electrons, okay? Now talk to me about sulfur. Sulfur has how many protons? 16. Okay. And let's do S2+ for a minute. 14, right? Because we're talking a third ionization energy, right? Okay. Which one of these is it going to be harder to get an electron from, and why? It's going to be harder to get it from here. isn't it?
Yes.
Because what does this have?
Electrons.
More protons. And aren't we looking, when we get Ca2 plus, that's on 3p, just like this is on 3p, right? Aren't these electrons going to be pulled in a little tighter than those electrons, right? Because we know it gets smaller going left to right across a period. But now they're in the same period, okay? So this is going to have a higher third ionization energy, okay? We good there? A little bit? I know. All right, one more idea, and then we're done. I just want to, and then you're in the exact same place as the other class period. And no more sample problems. We're just going to talk about this. Electron affinity. What do those two words mean? What's affinity? It's a love of something. Yes. Okay. So like I have an affinity for Fridays. I do not have an affinity for Mondays. Okay. So an affinity is a love of something. And an electron affinity would specifically be a love of electrons. Okay. Who loves electrons more than anybody else? Who wants one just so bad?
Protons.
No.
Halogens.
Halogens. Which halogen? Which halogen just wants an electron so bad? Which one? Who wants it the most? Fluorine. The small one. Who just, I mean, they all just need one more, but like, one more for fluorine would be a big deal, wouldn't it? Right? I mean, one more for chlorine, it's a big deal, but not as big of a deal as fluorine. You know, it has so many anyway. But fluorine, one more, that's such a big deal. Okay, electron affinity is the opposite of ionization energy. It's who wants the electron, not giving it up. Who breathes the biggest sigh of relief when it gets the electron? Fluorine, I got an electron. What's it doing with energy? It's releasing it, right? Electron affinity is releasing energy, like, I got it. Ionization energy, it has to go in, right? Energy goes in, that's endothermic. For electron affinity, it comes out, that's exothermic, okay? So, look at the trends, see if it makes sense. Remember, the negative signs just indicate releasing, right? So look at the numbers, okay? Compared to lithium, what would you say about fluorine's ionization energy? Or electron affinity? High, right? It's a lot higher. So the love of electrons increases big time, left to right, okay? Down the column, what happens? It mostly decreases, but it's not perfect, is it? Okay. I know, there are some blips. There are some blips.
Does it always
Okay.
increase one down and then decrease the rest of it?
Well, like, that's a, no, not necessarily.
No, but I mean,
There
like, from like the first period to this, or I guess that's the second period to the third
right.
period.
Yeah,
Does
like
that always
this
go
is
up?
slightly higher. Right, and probably because there are no, yeah. So, similar but not a perfect trend like ionization energy. Okay, now, listen. Shh. Your problems. Can we talk about those for a second? The like ones I assigned you, not your life problems.